in the last class. So we have learned about Maxwell's equations, which governs all the electromagnetic phenomena in nature, and which also predicts the existence of electromagnetic waves, which should propagate with a constant speed, that is 3 into 10 power 8 meter per second in vacuum. And naturally, the question which was quite perplexing is that in the last quarter of the 19th century, how to define the speed of light? I mean, what is the frame of reference with respect to which you will define this speed of light? So that was the reason why this Michelson-Morley interferometer was designed. This experiment finally showed that there is no such hypothetical medium like ether with respect to which the speed of light can be defined. So naturally, the next question was that everything, all the laws in mechanics was basically, this underlying laws of mechanics were provided by Newton's law, and we have already seen that Galilean transformation is not compatible with Maxwell's equations, because Maxwell's equations they do not remain invariant under Galilean transformation. And that implies that the laws of physics is frame dependent. That means you can actually distinguish one inertial frame from other by just looking at the laws of physics, by conducting some experiment inside the inertial frame, which is quite contradictory. And the next thing is that Galilean transformation also says that there should not be anything like magnetic field. Why I will discuss this thing gradually. For the time being, I will just state one example from which you can at least infer that magnetic fields cannot be possible in Newtonian mechanics. So let us imagine 2 point charges, say Q1 and Q2. Both charges are moving, say, along the x-axis with the same velocity, say v, okay, in some laboratory frame. And if I ask you what is the force acting between these two charges, so they are moving along the same direction, and suppose they have they are say separated along the y-axis at a distance, say r. So this distance r is along the y-axis, and both the particles are suppose moving along the x-axis. Fine. And if I ask you what is the force acting between these 2 point charges, so naturally, you will recall the Coulomb's law. If you know the two charges Q1, Q2, and then 4 pi epsilon naught r square, that is the force acting between the two charges. Now, you see, in Galilean transformation, what we have seen is that you can calculate the relative velocity between the two frames. If you have a particle moving in one frame, you can calculate the velocity of the particle in another frame. But what about the acceleration? We have already seen that the acceleration remains same, and so as the force. Right. So if I ask you what is the force acting between the two particles, so you will naturally say that that's given by the Coulomb's law. Right. And if I go to another frame, suppose some another frame S prime, which is moving with respect to these two particles with some other velocity, say u, along say x-axis, and then if I try to measure the force in that frame, what will be my conclusion? And naturally, if the acceleration is same, force is same, then you should say that okay, the force is same. That means, you see, what is the expression for the force due to magnetic field? You have you already know about Lorentz law, that is Q times E plus V cross B. So the force due to magnetic field depends on the velocity of the charged particle, right? But in this case, it will be frame independent. There should not be any such force which should depend on the velocity of the charged particle, right? It should be same, acceleration is same, so force is same. So naturally, in Newtonian mechanics, you do not see something like magnetic field. Okay, although this is a very brief description of the problem, I will gradually enter into this, because existence of magnetic field from the perspective of relativity itself is a very interesting phenomenon. Why magnetic field exists in nature, right? That's a very interesting question, and we have to understand that we have to think this in terms of relativity and the nature of electric and magnetic field. Okay, whether they are separate phenomena or they are same phenomena, of course they are interconnected, but how do we perceive them? how do we explain them in the relativity? And I can assure you that if you accept that there is no such thing like special relativity, then there should not be any magnetic field. So magnetic field purely arises due to relativity, special relativity. Why and how, that I will explain after a few classes, not right now. So for the time being, so let me just discuss the basics of relativity. I hope these things are already known to you, but still, I would touch upon the basic concepts, because the entire framework of relativistic electrodynamics that depends on relativity. Unless you understand the relativity very clearly, it is difficult to understand the deeper aspects of it. So I will discuss about the known things today. Not any new things. So what we have learned from special relativity, so we have two postulates. The first one tells us that the laws of physics should be independent of inertial frames. That was also highlighted by Poincaré before Einstein, right? So this is a law which basically assures you that laws of physics should be same. So there is no special status attached to any inertial frame in the universe. So all inertial frames are equivalent. Now, if you look at the this first postulate carefully, you may find the second postulate already hidden inside it. Because, okay, let me explain it step by step. First of all, if you look at the Maxwell's equation, it already tells you that there should be an electromagnetic wave which should propagate at constant speed. Right, so c is the speed of light or electromagnetic wave, which is constant. That is already claimed by Maxwell's equation. Okay, someone is typing the screen দেখতে পাচ্ছি না, আমি কোনো স্ক্রিন এখন দেখাইনি, right? Okay, so don't get confused. I'm কোনো স্ক্রিন দেখাইনি, I'm just discussing. Okay, I will come to screen later, right? আমি কিছু জেনারেল ডিসকাশন করছি, আমি স্ক্রিনে পরে আসছি, right? So lightest speed যে constant, so this is universal. Universal. It's a law of nature. It comes from the Maxwell's equation. Okay, it is not an imposed fact. Light of speed constant hote hobe ba ei hote hobe. It's not an imposed fact. It is purely coming from Maxwell's equations, right? And if you believe that the laws of physics should be frame independent, it should not depend on one frame or the other, then the speed of light is constant. It is governed by Maxwell's equation. So if Maxwell's equations are invariant, then so should be the light speed of light, isn't it? So relativity is already hidden in Maxwell's equation, and it only requires some insight into the problem, right? So Einstein was that kind of genius who actually who was capable of understanding this, and all the other physicists failed, specifically at that time. So if laws of physics are invariant from one frame to other, so should be the speed of light. And if that is the case, the first postulate tells you that the laws of physics are invariant. So second postulate is what? It is telling you that the speed of light should be constant in all inertial frames, irrespective of the motion of the source or the observer. Right? So that is the speed of light is constant. It is coming directly from the Maxwell's law, right? Maxwell's equations. So if I believe in the first postulate, then that is already implied. But anyway, there is you can actually restate the second postulate maybe in a slightly extended way, that there is a speed limit in the universe. So light is the fastest runner. There is no other particle or any physical entity which can run faster than this. This is something new, because Maxwell's equation only tells you that what is the speed of light, 3 into 10 power 8 meter per second. It is not telling you that is the highest speed or lowest speed or whatever it is. So that is something we have to accept, that it is the upper limit in this speed. So in Newtonian mechanics there is no speed limit, right? Because you can have any speed. A particle is moving, and if you are moving with a speed, say with if you have one particle moving with 2 into 10 power 8 meter per second, and other frame is moving with say 3 into 10 power 8 meter per second, then it can surpass the speed of light. That is possible in Newtonian mechanics. But relativity clearly states that the speed of light is the upper limit, right? And that number is fixed in the universe. Whatever frame you choose, wherever you go, doesn't matter. That is a constant, and that constant is a consequence of Maxwell's equation. So everything, like whatever I have stated, is already ingrained in the Maxwell's equation. Okay, definitely this upper speed limit is something which you have to add into the picture. Now, Okay. Now you already know about Lorentz transformation. It is not something very new to you because you have already done your course in relativity in BSc. So it's not something very new. And but I told you probably in the last class that initially this Lorentz transformation was derived by Lorentz without any insight of relativity, because he was trying to devise a or propose a physical mechanism which can explain the null results of Michelson model experiment. What he was thinking, both Lorentz and Fitzgerald, that probably the motion through ether contracts the arm of the interferometer, and it contracts by exactly that amount which can explain the null result. So they were trying to propose a new transformation which can explain this, but they have no physical mechanism, how that contraction takes place, what is the force acting on the interferometer, nothing like that. So it was a empirical transformation proposed by Lorentz. Now see, once you accept the two postulates of special relativity, there are multiple ways of deriving Lorentz transformation. I am not going to do that trivial thing. That's an algebra that you can find out any textbook for BSc students. So, but again, there are multiple ways to derive Lorentz transformation, and possibly this is known to you. So let me start from Lorentz transformation and then gradually build the story. So now I am going to the presentation. Till now, I was not showing any presentation. Okay, so I'm going to the presentation mode now. If you cannot see anybody of you, please let me know. 1 minute. What happened? Can you see the presentation? Hello? Yeah.
Yes, sir.
Yeah. So actually, I'm not preparing a slide at this moment, because last day some of you have mentioned that because if I don't show the mathematical steps elaborately, then probably you may have some confusion. So that's why I'm writing. I'm preparing the slides by hand and then scanning it. I have ordered a tablet. Unfortunately, that was returned, and then again I reordered. Hopefully within a week or 2 week I will get that. আমাদের একটা ফরচুনেটলি একটা এখন যেটা আমাদের যা শোনা যাচ্ছে যে তোমাদের এই সেমিস্টারটা মার্চ পর্যন্ত এক্সটেন্ডেড হবে, সুতরাং সাফিসিয়েন্ট অ্যামাউন্ট অফ টাইম আমাদের হাতে আছে। সো আমি খুব তাড়াহুড়ো করছি না, গ্র্যাজুয়ালি যেভাবে অন্যান্য বছর পড়াই সেভাবেই পড়ানোর চেষ্টা করব, কারণ হাতে সময় আছে আমাদের নভেম্বর, ডিসেম্বর, জানুয়ারি, ফেব্রুয়ারি, রাইট? মার্চের হয়তো কোনো একটা সময় ক্লাস সাসপেন্ড হবে। সো ইটস উই হ্যাভ সাফিসিয়েন্ট অ্যামাউন্ট অফ টাইম। ওকে, অবশ্যই এই মাসে কিছু ক্লাস নষ্ট হতে পারে বিকজ অফ দিস পিজি অনগোয়িং পিজি অ্যাডমিশন, বিকজ দের আর লট অফ ওয়ার্ক টু ডু। 20 তারিখের মধ্যে কিছু অ্যাডমিশনের ফাইনাল লিস্ট বানাতে হবে, পরীক্ষা নিতে হবে। সো কিছু ক্লাস হয়তো নষ্ট হতে পারে, বাট এগেন উই ডোন্ট নিড টু ওয়ারি। আমাদের যা সময় আছে তাতে আমরা যদি পরের ক্লাসগুলো সব কটা করতে পারি তাতে সমস্যা হওয়ার কথা নয়। ওকে, সো লেট মি স্টার্ট. So Galilean transformation, here I have written this again. So in Galilean transformation, what was the concept? So if you have a clock and a meter scale in your hand, and you are standing at a fixed place in your inertial frame, basically you can measure the length and time in any other inertial frame without any problem. So space and time are absolute in Galilean transformation. Space in the sense that length is not going to change. If you measure a length of say a meter scale in one reference frame, it is going to remain same in all other inertial frames. And so is the time. Time is something absolute in Galilean transformation. So here I have written this transformation t prime equal to t and the other. So in this case, of course, what I would suggest you to imagine that there are two frames. One frame is at rest. Let us call that frame as S. And another frame S prime, which is moving with respect to S with velocity v, uniform velocity v along the x-axis. In that case only you can write the transformation in this way. And if we write that transformation in the matrix form, then this is the Galilean transformation, because time is absolute. So I have written t prime as the first coordinate. So each and every event in relativity, whether it's Newtonian relativity or specifically in special relativity, you will see that each and every events are labeled by 4 numbers, right? So time and the 3 spatial coordinates. And I have not talked about 4 vectors yet, but this is the beginning. Yeah. Any question? Hello? Anyway, so we have time and 3 spatial coordinates. and we are looking for the transformation of these four numbers from one inertial frame to other. So Galilean transformation is not the correct choice if you want to incorporate the Maxwell's equation in this framework. So that's why Lorentz transformation was proposed. And here I have just written the same example, that is S prime is moving with respect to S along the x-axis with velocity, uniform velocity v. So these are the four, so x prime, y prime, z prime, and t prime are the space-time coordinates of an event in S prime frame, which is moving with velocity v along the x-axis, and x, y, z, and t are the space-time coordinates of the same event in the frame S, which is at rest with respect to S prime. No, sorry, not with respect to S prime, it is at rest, right? With respect to S prime, something else will, because if you go to the S prime, you will see that S prime is at rest and S is moving with velocity minus v along the x-axis. Okay, so one frame is at rest, another frame is moving. So I am talking in terms of an observer from S frame, and how do I get the coordinate of the event in the S prime frame? So these are the transformation which relates the space-time coordinates in the two inertial frame. And if you rewrite v, you define a variable beta, which is v by c, which is well known to you possibly, and gamma, which is 1 over square root of 1 minus v square by c square, which is called Lorentz factor. So you can see that these this transformation equation can be written in this form, right? So, because here what I have done here, I have divided by I have divided v by c and multiplied c with t. So Ct is a number here, and v by c, that's beta, and 1 by square root of 1 minus v square by c square is gamma. So x prime equal to gamma times x minus beta ct. Y prime and z prime, obviously they do not change because there is no motion along y or z axis, it is moving along the x axis, so these two coordinates remain unchanged. And the time coordinates similarly, if I multiply c on both sides, ct prime equal to ct minus, if I multiply ct, one c will be cancelled, so this will become v by c, that is beta, and then x, and the first term becomes ct, and already this 1 over square root of 1 minus v square by c square term is outside, that is gamma, right? So these are the same transformation, but for the sake of simplicity, from now onwards we will be using these equations which are in terms of beta and gamma, not in terms of v and x and so on. No, v and not in terms of velocity here. I mean, it's beta, simply beta and gamma. And if I ask you what are the range of beta and gamma, you can clearly see beta is a number which must be smaller than 1 because the upper speed limit is c. So beta, when v is c, that's 1. So it should be a number which is smaller than 1. It could be 0.01, 0.001, or whatever, less than 1. And what about gamma? Gamma is Lorentz factor. Clearly you can see that this will be smaller than 1. So definitely this will be larger than 1. So gamma is a number which is larger than 1. Could be 1.01, 1.001, or 10, or 100, 1,000, million, trillion, whatever. Gamma can go up to infinity, right? Starting from number, so obviously v is 0, that's 1, right? So starting from 1 to infinity, that's the range of gamma. And if I write the Lorentz transformation equation in the matrix form, we have this form. Specifically for the transformation along the x-axis, right? So ct prime, x prime, y prime, z prime are the space-time coordinates of the event in the prime frame, and these are in the unprime frame, and this is the Lorentz transformation matrix. And you can clearly see here gamma minus beta gamma, there is symmetry, nice symmetry here, right? Space and time are I mean, you can see that these are basically and that's why in the relativity you see the space times are basically, they form a continuum and they are not separate entity. So this is a specific case where the prime frame is moving along the x-axis. Of course, if it is moving along the y-axis, then definitely this will be gamma, but this will be 1, this will be minus beta gamma, right? This will be 0, this will be 1, this will be 0, this will be minus beta gamma. This will be again 0, this will be gamma, and this will be 0. If it is moving along the z-axis, then this two term will be 0, 0, 0, this will be minus beta gamma, right? This will be again 0, 0, this will be minus beta gamma. This two number will be 1, 1, here it will be gamma. if it is moving along the z-axis. Simple. I mean, you can just rewrite this. I mean, if it is moving along the z-axis, then definitely x prime, y prime won't change. Only z prime will change. If it is moving along the y-axis, then of course x prime, z prime will not change. You write y prime equal to gamma into y minus beta ct. So it's simple. So this is Lorentz transformation. And we can write down transformation for other directions as well, following the same this structure of the equations. And this is the inverse transformation. If I go to the frame, moving frame, the prime frame, if you move to the prime frame, that frame will, what that frame will see, that the other frame which was at rest, that is S, the frame S, that should move along the minus x-axis with velocity v. So you just have to replace this v with a minus v in the transformation. That's why this is minus v by c. If I put minus here, minus becomes plus, so beta gamma and so on. Nothing changes. It is just the perspective of the observer. If I go for another frame, that will find itself to be at rest, the other frame is moving. So because there is no inertial frame, speed of light is constant. Whichever frame you go, doesn't matter how you are moving. So that ensures the equations of relativity. We'll gradually discuss this. Okay, this is just simply Lorentz transformation which are already well known to you. So I have just repeat. This is a kind of repetition. Fine. And Lorentz transformation, or sometimes called Lorentz boost, if it is applied to a specific direction, can be combined. So suppose I give you one particular example. Suppose this is one frame, so I am discussing here two successive Lorentz boost along the same direction. Suppose this is one frame S which is at rest, and consider another frame S prime which is moving along the x-axis with say velocity v1 or v1 by c, that is beta 1. Okay, and there is another frame which is, let us call that S double prime, which is moving with respect to S prime frame with velocity v2 or beta 2 along the x-axis. Now someone asks you what is the velocity of this frame with respect to that frame. Naturally you will apply the velocity addition formula, which is already well known to you, but I will show you that by just simply by applying Lorentz boost you can find out that. And actually Lorentz boost, when you apply in the same direction, they actually commute. So if I want to relate the space-time coordinate in this frame with that frame, how do I relate that? Because if I try to relate the coordinates of this frame to that frame, that comes up like this, right? This one, ct prime, x prime, y prime, z prime. Since it is moving with respect to this frame with velocity beta 1, I have this transformation for that, and ct, x, y, z are the coordinates in the non-moving frame or the frame at rest S. Right. Similarly, you can connect this frame to that frame where the Lorentz transformation, in this case, the velocity is v2 or beta 2. So I write the transformation equation in this manner, right? And now our goal is to relate the quantities in this frame to that frame. So here you can see the double prime quantities are related to the single prime quantities via this equation, and the single prime quantities are related to the unprimed quantities via this equation. So if I put the single prime quantities, expression for single prime quantities here, I get this expression. So it is simply matrix multiplication. You can do the multiplication and find out the individual components of this matrix, which is nothing but this one. You can do this exercise, which I have not done here. It's straightforward. It's matrix multiplication of these two matrices. So you can see again we have 4 numbers at this corner. Other two diagonal elements are 1, and all the other diagonal elements are 0. And this simply tells you that I can again rewrite the transformation between this double prime frame and the unprimed frame in the same fashion as Lorentz transformation. So if I rewrite or redefine the first number to be equal to gamma 3, and this is to be say beta 3 gamma 3, then we can find out a relation. So suppose gamma 3 is gamma 1 gamma 2 1 plus beta 1 beta 2. Gamma 3 is just a number we are defining, right? And suppose see the negative sign here, minus minus, very similar to the Lorentz transformation, right? So and beta 3 gamma 3 is suppose gamma 1 gamma 2 into beta 1 plus beta 2. So if you just divide gamma 3, if you divide this equation by that equation, you find beta 3 equal to beta 1 plus beta 2 plus divided by 1 plus beta 1 beta 2. That is nothing but the law of velocity addition in relativity. right? So basically this is telling you what should be the velocity. Suppose this is a particle, you can imagine this to be a particle which is moving with velocity v2 in this frame. So you want to figure out what should be the velocity in this frame. So of course there will be minus sign if you calculate the velocity from this frame, but this is the opposite, it is looking from this frame to that frame, so that's why it is plus. The two terms, if I bring this matrix in the first place and this matrix in the second place, that doesn't change the expression, this final expression. So they commute under this basically exchange of their position. But I will leave an exercise for you. Apply two Lorentz boost, one along the x direction, another along say or along the y direction or z direction, and try to calculate the doesn't work there. They will not commute, right? So two successive boosts along orthogonal direction, they will not appear like a boost. It will be some translation times some rotation. So you have to understand what rotation does mean here. But this is a simple exercise. You can try it yourself. In this case, both the Lorentz boosts are along the same direction. So that's why they commute. And why they do, I mean, when it is the orthogonal direction, they will not commute because they are not boost. We will discuss this again. Okay, I'm just mentioning this to you. And till now I have only discussed about the transformation, Lorentz transformation along the x direction when the prime frame is moving along the x direction, but that need not be the case. The prime frame can move along any arbitrary direction, so you should be ready with a transformation equation which can be applied to an arbitrarily moving particle, right? So this is definitely a simple thing, because matrices multiplication and all that becomes very simple, and when you have to multiply matrices of this say 4 by 4 matrices to, and you have to manipulate things, then if you have all the elements there, it becomes a bit complicated. Okay, but the physics doesn't change, so that's why we are using this example. Okay, but still we should discuss the general thing. So this is the formula for a general Lorentz transformation. So how do we derive this? So for example, let me just again take two frames. One frame is S frame, which is at rest, and consider another frame S prime, which is moving with velocity beta or v along some arbitrary direction. So it has three components: beta x, beta y, beta z, or vx, vy, vz. It can move along any arbitrary direction. Now suppose we want to relate the space-time measurement in these two frames. Let us call the spatial coordinates in the prime frame as say r prime, t prime, right? Or ct prime if you take the Lorentz transformation. So t prime and r prime. R prime means the components are x prime, y prime, z prime, and r and t are the coordinates of the same event in the unprimed frame. So here I have written the spatial coordinate of the event in the unprimed frame as r vector equal to r parallel plus r perpendicular. What do I mean by parallel and perpendicular? Here I have taken the components of this position vector along the direction of velocity and perpendicular to the velocity. So r parallel is the component of the position vector along the velocity, and this is perpendicular to the velocity. And now if we apply the Lorentz transformation to this position vector, that means we want to calculate the position vector, same position vector in the prime frame, then you see the r prime is the coordinate of the event in the prime frame. Now you see this perpendicular component will not get affected. We already know from Lorentz transformation, so it is the only parallel component which is affected by the relative motion. So perpendicular component remains unchanged, and parallel, for the parallel component we have applied the usual Lorentz transformation, gamma times r parallel minus beta ct. You see this formula has been already derived in the previous case, right? This is the, you see, x prime equal to gamma into x minus beta ct. So I am using the same expression here, gamma into r parallel minus beta ct, right? And if I again write r perpendicular to be equal to r minus r parallel, so I have just used this equation here, plus gamma times r parallel minus beta ct. Now you can take r parallel common from these two terms, that gives you r plus gamma minus 1 times r parallel minus gamma beta ct. So first term is the position vector r plus C. R parallel, I told you that R parallel is nothing but the component of R along the direction of velocity. So to get that, you have to take a dot product of R with the unit vector along the velocity. So unit velocity, I mean the direction, beta by beta is the unit vector along the velocity vector beta. So if I take a dot product of R with this, we should get back R parallel. Magnitude of R parallel. Dot product is a scalar thing, so that will give you magnitude of R parallel. But R parallel have a direction as well. That is given by the unit vector along velocity. So beta by beta is the unit vector which gives the direction of this direction vector of R parallel, and this gives you the amplitude. Gamma minus 1 remains unchanged here, right? And the last term is gamma beta ct. Now I have just written the components of each of the vector explicitly. So R is x cap plus y cap plus z cap. Beta is again a vector. I told you it has components beta x, beta y, and beta z. So beta x, so beta is something you could have taken it outside as well, but I have kept them in the denominator. Sorry. So beta x is the x component of velocity. So dot product beta x by beta, beta y by beta, beta z by beta. This is gamma minus 1 divided by beta. Beta is a vector, so beta x cap, beta y cap, beta z cap. And the last term again, I have written this beta in terms of its component, beta x cap, beta y cap, beta z cap times ct. Now you see in okay, I have not talked about the time coordinate. And time similarly, ct prime will be gamma times ct minus beta dot r, right? Earlier what was this component? You see beta x, because they are moving in the same direction, but here it is in arbitrary direction, so it is beta dot r, and beta is again a vector, so you can write beta x beta, you have this the dot product beta x beta y beta z. So we have the entire transformation. Now we want to write that in a matrix form. You see, in Lorentz transformation, this is time coordinate, right? This is time, this is time space, this is time space, this is again time space, this is space time, this is space time, this is space time, and all the remaining these 9 terms are space components, right? So if you look at these equations, we can figure out what are the corresponding terms. You see time, you see this is gamma, only one factor is there with time, this is gamma. What is time space? You see gamma times beta x, this one. This is gamma times beta y, this one. Gamma times beta z, of course with a negative sign. Don't forget the negative sign here, negative sign, right? What about the space time? You can again see this equation. It is the space, and what is the time? This is t. So space time, you see gamma beta x, the same gamma beta x or beta x gamma, whatever. Beta y gamma minus beta z gamma. What about the space component, x component? To get that, you have to multiply all the terms and separate them out. You see, this is x component 1. This will be multiplied with this one, so this will be gamma minus 1 beta x square by beta square, and then that's the x component, pure x component. So that's why I've written 1 plus gamma minus 1 beta x square by beta square. What is xy component? You can again figure out. You see, this is x multiplied with the y component, right? So beta x beta y divided by beta, right? This is gamma 1 beta x beta y divided by beta, and there is also beta, so beta square, so beta x beta y by beta square. You can similarly find out all the space terms. That is not difficult, it's a trivial exercise, you can find out it yourself. This will be gamma minus 1 beta x beta z by beta square, and so on. So only difference with the diagonal terms, there will be 1 plus term, 1 plus gamma minus 1 beta x square by beta square, 1 plus gamma minus 1 beta y square beta square, and so on. So you should know this general Lorentz transformation, because this describes the motion of the inertial frame along any arbitrary direction, right? So this is a general expression for Lorentz transformation in arbitrary direction. And we should also remember that Lorentz transformations are only applicable in case of inertial frame. So you can only relate the space-time measurements between two inertial frames via this transformation. And we have already seen that Maxwell's equations are invariant under Lorentz transformation. So they provide perfect framework for describing the relativistic, I mean, electrodynamics. That is the relativity. That means the two postulate of relativity provides you the framework where Maxwell's equation remains invariant. That is, they are the fundamental law of nature, and they do not depend on any particular frame of reference. So let us begin from this discussion of Lorentz transformation and some of its consequences, because these consequences are very important in order to understand the origin of magnetic field and electric field. Unless you understand this clearly, it will be difficult to grasp the other things in this topic. Okay. Okay, so let me just now write down how the space-time intervals. So till now I was discussing about the space-time coordinates only in the two frames. Now I am going to talk about the space-time intervals. So instead of taking one particular event P in the two frames, right now I am talking about the two events, the P1 and P2. Right, and so if I take two events P1 and P2 and label by say x1, y1, z1 and ct1, and another x2, y2, z2 and ct2, and then calculate the space interval and time interval between the two events, then how that space-time interval between the two events are related in the two inertial frames that we were discussing about. So delta x prime in a very similar fashion. So here again I have not used gamma and beta, just to discuss a couple of things which should be more clear in this kind of expression. Otherwise we can have also use beta and gamma, doesn't matter actually. So delta x prime is delta x minus b delta t divided by square root of 1 minus b square by c square. Similarly, delta t prime is delta t minus b by c square delta x by square root of 1 minus b square by c square. Here delta x and delta t are space-time interval between the two events in the unprimed frame, and delta x prime and delta t prime are the space-time interval between the two events P1 and P2 in the primed frame. If I look at the same two events from the unprimed frame, I should have a plus sign here, because from the perspective of the primed frame, the unprimed frame is moving with respect to that frame with velocity minus b along the opposite direction. So that's why this minus b becomes plus b here, right? And using this set of transformation, we can easily see what should be the velocity addition formula, right? How the velocity of particles should be added in special relativity. This is again also known to you, right? So how do you define velocity? It's infinitesimal small change in position, and the time that is delta x delta t, and in the prime frame delta x prime delta t prime. So suppose I want to calculate the velocity of a particle, say the particle moved from say p1 to p2 in time interval delta t prime, so it has traversed a distance delta x prime. So what should be the velocity of the particle, right? So P1 and P2, suppose it's the initial and final position of a particle, right? So that's delta x prime by delta t prime, which I have substituted from here. So Lorentz factor gets cancelled. Delta x minus b delta t divided by delta t minus b by c square delta x. If you simply divide by delta t, all the terms divide by delta t. So that's u, that's v, that's 1, and this one will be again delta x by delta t is v. So sorry, u. We are labeling delta x delta t as u. That's the velocity of the particle. You see, remember, v is the velocity of the frame which is moving with respect to s. S prime is moving with respect to s with velocity v. So v is different. U is the velocity of the particle which moved from space-time coordinate p1 to p2, right? So that's the velocity of the particle. So that's u. Delta x by delta t is u. So u prime and u are rated by this relation, right? So that's the usual velocity addition formula. Earlier in the previous slide I showed you beta 1 plus beta 2. That is nothing but this opposite perspective. You have the plus sign here, right? If you see it from that frame, it will be plus. U equal to u prime plus v, and then 1 plus u prime v by c square. And if we use this equation, we can clearly see that you cannot surpass the speed of light, right? So suppose you have a light pulse in the S prime frame. So suppose a light this two events P1 and P2 denote the propagation of a pulse from some space-time coordinate P1 to some space-time coordinate P2 in the prime frame. So with velocity c. So in that case, I have to put u equal to c in this expression for the velocity addition formula or velocity transformation formula, And interestingly, we find of course u prime equal to c. That's the basic framework of relativity. So it is built in such a fashion that the speed limit is c. Whatever speed you use, 3 by 4 c, 5 by 2 c, 2 by 5 c, or any other velocity you can take. Here I have taken the extreme, u equal to c. So if u equal to c in the unprime frame, you will see the prime frame also that's equal to c. That is inbuilt in relativity. That's the consequence of the postulate that has that is the base of relativity, right? Again, of course, if you take if you write that in the terms of the prime frame quantities, so u equal to u prime plus v here. So again, if you put u prime equal to c from so suppose the particle is, in this case particle was moving with velocity c in the unprime frame. In this case the particle is, sorry, it's not particle, sorry, it's light pulse which is moving with velocity c in the prime frame. Then again, if you use this transformation, you will get again c. So whichever frame you go, the speed of light is constant, and that's the basic tenet of relativity. See, all that confusion that we have in relativity arises purely from this fact, right? Because this length contraction, time dilation, all these are consequence of this, right? Because there is no such no extra force which is acting and contracting something, right? So I will discuss length contraction soon. So it is purely a consequence of this fact, which we have a hard time to actually digest, that why there is a speed limit. And I again told you that speed limit is not something imaginary or fixed, as that comes from the Maxwell's equations, right? That is telling you that c has to have a value of equal to 3 into 10 power 8 meter per second. Why it is not 3 into 10 power 2 meter per second? We don't have an answer, right? That's nature. That's nature has provided us. That's value is given to us, right? You can't change that. And once you take this as a fact of nature, there is a speed limit in nature. So I mean, a speed limit cannot be arbitrary. You cannot go to an arbitrary speed. There is a speed limit, and that what defines the nature of space-time. Right. So actually then the Lorentz transformation basically tells you how the measurement of length scales and the time scales transform between the two inertial frames, given the fact that the speed of light is constant, nothing else. Relativity is all, I mean, if you just summarize relativity, this is just it, right? All other things are consequence. But again, since those things doesn't go along the common sense, so that's why you have a lot of confusion. So let us explain a couple of things which are related to Lorentz transformation. So time dilation. Okay, so somebody asked me in the last class what is the origin of time dilation, why there is time dilation. Okay, so let us first understand clearly what time dilation is about. Again, I have taken a simple example where one frame is at rest, another frame is moving with velocity beta along the x-axis. Okay, forget about this clock. Okay, I have mistakenly drawn two clocks here. Okay, suppose there is only one clock here which is at rest in the S frame, right? So this clock is at rest, remember. Okay, and suppose we know that the time measured in the rest frame is called a proper time, right? So let us consider a proper time delta t equal to tau 0 measured by an observer in the unprime frame. So some observers, suppose he or she is sitting at say x equal to 5 with a clock, and the person measures proper time interval delta t equal to tau 0, right? And since the person is sitting at a fixed location, the interval, when you are measuring time interval, the space coordinate of the clock is not changing. The clock is sitting at rest, only time is changing, right? So if I consider two events to be the measurement of the time in the beginning and the measurement of time at the end of the interval, then only time is changing, space is not changing. That's why delta x equal to 0. So since the clock is at rest in the unprime frame, delta x equal to 0 and delta t equal to tau 0 is the proper time interval measured by the observer in the unprime frame. Now if I ask an observer who is moving with velocity beta along the x-axis what should be the time interval measured by him or her, we have already got an expression here for delta t prime. So see, delta t prime is delta t minus v by c square times delta x divided by 1 minus v square by c square. So if we know the time interval in the other frame and the space interval between the two events in the other frame, we can get the time interval in the prime frame. So what is delta x? I told you in this particular example, delta x equal to 0 and delta t equal to tau 0. That's the proper time. So if I just put that expression, delta x equal to 0 and delta t equal to tau 0, then we have this expression, delta t prime equal to tau 0 divided by 1 minus v square by c square. Okay, that's an algebraic manipulation. That doesn't tell you why the time is going to be different, right? It clearly tells you that the time interval measured by the two observers are not same, right? Proper time is the longest time. If you measure time in any other frame, so right, so that's why clock appears to be slow. See, 1 by square root of 1 minus b square by c square is called the Lorentz factor. That's gamma. I told you the value of gamma is always larger than 1. So delta t prime equal to gamma times tau 0. So tau 0 will be delta t prime by gamma. So that's going to be smaller than that. Right? If you divide the delta t prime by a larger number than 1, that's will be smaller. So, so the observer in the prime frame would infer that the clock in the unprimed frame runs slow. So what is the reason? Regions is simply, you see, in relativity, space and time are not separate entity, which is a fixed notion in our head, right? We have a fixed notion, space and time are separate things. They are not separate because they are mixed up in Lorentz transformation. Space and times are mixed up. In Galilean transformation, space times are not mixed up. In Lorentz transformation, they are mixed up. So you see here in this frame, the clock is not moving. Right, so if you measure the location of the clock at the end on beginning of the interval, they remain same. So delta x equal to 0. There is only time difference. But if I look from this frame, since this frame is moving, what he or she will find that he is at rest, but this frame is moving along this direction with velocity minus v. That means when the observer from this frame look at the beginning and the end of the event, he or she will find that not only the time is different at the to end of the event, but also the spatial coordinates. Suppose আমি আবার বলছি এখানে যে ধরো না ঘড়িতে 10টা 10 আর 10টা 20 10 মিনিটের গ্যাপ দেখা হচ্ছে, so the intervals begins at 10:10 and it finishes at 10:20. Now if I go to this frame, so when the clock is at 10:10, the coordinate of the clock is somewhere say x equal to 5. But when it is 10:20, since from this frame is moving along this direction. So at the end of the event, this clock has moved to another position. That means from this frame there is a spatial interval, right? And how do I find that? It's simple. If I want to find out the space interval delta x prime, you see delta x is equal to 0, right? Delta x equal to 0, right? So and in this frame, if I want to find out what is delta x prime, you see this is minus v into delta t prime. This is minus v into, sorry, this one, sorry, yeah. This is delta x. So delta x prime equal to minus, so this is v delta, this was 0, delta x was 0 in the unprimed frame, right? In the prime frame, delta x prime is not 0. It is something else. And what is that? To get that, I have to put a 0 here. If I put that to be 0, delta x prime is not 0, it is minus v times delta t prime, which is simply telling you that the two events are not occurring at the same place, and there is a spatial separation between the two events in this frame. In this frame, there is only time separation, no space separation. In this frame, you have a time separation as well as space separation. Naturally, the time difference that will be measured by the two observers will not be same. So if suppose you are not so you use this equation. Now let us use this equation. Both of the objects, suppose I can keep the clock here as well. Suppose a clock is at rest in this frame, and suppose okay, erase this clock. Okay, suppose there is a clock in this frame which is at rest, and this frame is moving along this direction. The things should be identical. So in that case, we will be using this transformation, delta t equal to tau 0 and delta t prime plus v by c square delta x prime. Now I told you in the prime frame, delta x prime is not equal to 0. Delta x prime equal to minus v times delta t prime. So if you put that, again you see delta t prime into 1 minus v square by c square divided by square root of 1 minus v square by c square. So you will have a square root of 1 minus v square by c square on the numerator. that again gives the same relation that we have obtained for the first case. So in one case we kept the clock in the first frame, in the second case we kept the clock in the second frame and tried to measure the time from both the reference frame. Whatever you do, both the observer either in S and S prime, they come to the same conclusion that the clock of the other person is running slow, right? That is because the proper interval is always the longest time, right? And in any other frame, since the time interval also is associated with a space interval, I mean time interval, and also there is a spatial interval that leads to the difference. And since in Lorentz transformation, if you look at the Lorentz transformation, you see delta x involves delta t prime, delta t involves delta x prime. So space and times are mixed up. They are not separate entity. If you have a change in the space interval, that is going to reflect the time interval as well, and the vice versa. So time dilation is simple consequence of this fact, because the speed of light is constant in all your cell frame, that leads to time dilation. And you see, time dilation and length contraction, they are not separate things. If one happens, the other is bound to happen. So what is length contraction? Again, I will go very quickly here. Length contraction, suppose there is a rod lying in the unprimed frame. So the rod of proper length, say L0, lying in the unprimed frame. And the prime frame is again moving with velocity beta along the x-axis. So I have just written down the transformation equations once again. Delta x prime equal to delta x minus b delta t by square root of 1 minus b square by c square, and similarly delta t prime equal to delta t minus b by c square into delta x divided by square root of 1 minus b square by c square. Here delta x equal to L0, suppose. Okay, let us call it the proper length of the rod in this frame L0. And the other person who is in the moving frame, suppose the length measured by him or her is L. Now we want to compare the length measured by the two observer, right? Now there is a important thing that you should be careful about: length measurement. So when you measure length, you see, you have to take the reading of the two ends simultaneously. Either you take assistance from your friend or whatever you do, you have to measure the length simultaneously, or you put some camera, whatever you do, you have to measure them simultaneously so as to get the proper length. Now, okay, that means in this case delta t, so suppose the measurement of the two ends are the two events, measurement of the reading at the two ends are two events. That means the time, if you have to measure the two reading of the two ends simultaneously, that means delta t has to be 0. There should be only delta x, that is nothing but the proper length. So delta x equal to L0, and delta t should be 0, because the measurement of length has to be simultaneous. The two ends, reading at the two ends must be taken at the same time. So that means delta t equal to 0. Well, so if I so this is again the same inverse transformation, minus plus sign, other than that they are exactly same. So now from the S prime frame, if someone measures the length of the same rod, he has to stick to the same principle. He or she has to measure the reading at the two ends at the same time. That means there should not be any gap between the measurement of the reading at the two end. So in that frame also delta t prime has to be 0. That's the fundamental definition of length measurement. Well, if delta t prime equal to 0 in this frame, you can clearly see, if I put a 0 here, delta t equal to v by c square times delta x, right? And what is delta x prime? Delta x prime is this. Delta x prime is nothing but the length interval. So delta x prime is equal to delta x minus v, and delta t we have already seen that delta t, if you ensure that delta t prime equal to 0 in this frame, that is not going to keep the time interval 0 in the other frame. In the other frame, you can clearly see delta t equal to v by c square by into delta x. Why? Why is this the case? Because from this frame, you are measuring the reading of the this two end, right? But from the perspective of this frame is moving along this minus x-axis with some velocity, minus beta, right? So when you measure this end and that end, the rod is not at rest; it is moving. So there is no way you can measure them simultaneously, because there is spatial separation between them. So light signal takes some finite amount of time to travel between this and this. So if I send a signal, suppose there is a mirror attached to the end. If I send a signal and time taken by the light to come back from here and here, they will never be same because there is a spatial interval, and this is also moving. So that means if I MCO, then the time interval between the two events are 0 in this frame, that is the events are simultaneous in this frame. There is no way you can ensure that the two events are simultaneous in that frame. That is the little bit of simultaneity. So delta t will be v by c square times delta x from this equation itself. I have just put delta t prime equal to 0. And if you use that in the first expression here, you get delta x prime equal to delta x minus v into this v by c square times delta x, because that is the delta t. And if you simplify, you get L equal to delta x equal to L0 is the proper length that we have defined. So L equal to L0 times 1 over square root of 1 minus b square by c square, and that is nothing but the 1 over Lorentz factor, that is L0 by gamma, and gamma is a number which is larger than 1. So L has to be shorter than L0, because L, when you measure L from this frame, that is L0 divided by gamma, which is a number larger than 1 less than infinity. So L has to be shorter than L0. So length contraction is again a consequence of the relativity of simultaneity, or you can also say the time dilation, because you see time is not same. In one frame delta t prime is equal to 0, another frame delta t equal to something else, and since space times are mixed up, so these are basically interrelated things. If there is time dilation, there has to be length contraction. If there is length contraction, there has to be time dilation. They are basically not separate things. We are looking them at separate in a separate manner. They are not separate, and that is the hardest barrier in understanding relativity. Because we are designed, our brain is hardwired in that fashion to think space and time in as separate entities, but that is not the case, right? So again, you may wonder, if I keep the rod in this frame and look it from here, I should have the same conclusion that the rod has been contracted from, if I look at from this frame. So that's why I have also repeated this exercise. So suppose the rod is here, and someone is trying to measure the length of the rod from this. So if the person is trying to measure the length of the rod from this frame, then again delta t has to be 0. So if you put a delta t equal to 0 in this equation, delta t prime has to be minus v by c square times delta x prime. And if you plug in that in this equation, you again come up with the same conclusion, that the length of the rod has to be shorter than what it is in its own rest frame. So that is called length contraction. And remember, this is purely a consequence of the geometry of space-time. There is no force acting on the rod which is contracting the rod or something like that. This is a pure consequence of the geometry of space-time. That's how the space and time are basically they combine with each other, and I will soon discuss this, because that's not an Euclidean geometry, right? And that's the problem, because our brain mostly is familiar with Euclidean geometry, because day-to-day life, everyday life, we mostly encounter the problems related to Euclidean geometry. And this is something different from that, and that's what the origin of the problem. And connected to this, I should also touch upon a little bit about the synchronization of clock, because I remember in last class someone asked me that how to synchronize clocks, and that's a very interesting problem. Although I will not go into detail of clock synchronization, because that's a vast topic and very interesting topic. I may get diverted. So if you are interested, then I can of course discuss it later. But for the time being, I will just mention a couple of things. Okay, how do you synchronize clocks, right, in your own frame? Suppose let us take an example. Say there are two persons, A and B, right? A and B, and say are sitting at two different locations, right? So at say the separation between the two persons is say L meter, okay, or L kilometer, whatever. So there is some separation between the two persons, L. Now, if I keep a light source between the two persons at a distance L by 2 from each of them, that is, if I put a light source just at the middle of the separating vector, say I keep a light source at a distance L by 2 from A, so it will be also L by 2 away from B. And if I ask the two persons to start their timer or adjust their clock when they receive the light signal, so I switch on a light which is lying L by 2 from each of them. So as soon as I switch on the light will reach both of the observer after time L by 2 times C, L by 2C. So as soon as they receive the signal, they adjust their clock, say 10 to or whatever time. I mean, it's just time. So both of them have the same time, right? That means last day I also talked about a grid where you can imagine a clock sitting at the grid corners, and then you can imagine such kind of light signal in between the grid points, and when you receive the signal you adjust your clock so that the time is same in all the grid corners. But wait, there is a problem. But before going to the problem, I should first tell you, because time dilation is also a fact of relativity, and so as the length counter. हाँ बोलो.
রাইট থেকে একটা ক্লাস আছে আমাদের।
ও ও আমি ক্রস করে গেছি, ফাইন, আই এম
হ্যাঁ
সরি.
স্যার।
2 মিনিট আমি ছেড়ে দিচ্ছি, 2 মিনিট, হ্যাঁ, জাস্ট 2 মিনিট,
ঠিক আছে।
জাস্ট 2 মিনিট, ওকে. তার মানে ইফ ইউ ওয়ান্ট টু সিঙ্ক্রোনাইজ ইউর ক্লক, সো সাপোজ, ওকে, লেট আস লুক অ্যাট দিস পার্টিকুলার পিকচার, রাইট? সাপোজ দেয়ার আর 2 পারসন, দুটো ক্লক ইমাজিন করো যেটা কিনা ওয়াই ডাইরেকশনে সেপারেটেড, রাইট? হ্যাঁ, তাহলে দেখো, তুমি যদি যে কোনো ফ্রেমে যাও, অন্য ফ্রেমে যাও, এই ভার্টিক্যাল ডিস্টেন্সটা তো চেঞ্জ করবে না, করবে কি? এটা চেঞ্জ করবে না, রাইট? বিকজ লেন্থ কন্ট্রাকশন only happens in the direction of motion. So imagine two clocks here and here, so the two person separated along the y direction, and then you are measuring, adjusting your clocks by light signals, so the clocks are synchronized. If the clocks are synchronized in this frame, they have to be synchronized in all other frames. The problem is simple. So that means synchronization of clocks when they are separated along the perpendicular to the direction of motion applies to all frames. But that will not be the case when the clocks are separated along the x direction. আমি এখানে একটা ক্লক রাখি, এখানে একটা ক্লক রাখি, এই যে মেথডটা বললাম সেই মেথডে সিনক্রোনাইজ করি ক্লকগুলোকে, তাহলে কিন্তু অন্য কোনো ফ্রেম থেকে দেখলে আমি দেখবো লাইট সিগন্যালটা এই ফ্রেমে আগে আসছে, ওই এই ক্লকের কাছে আগে আসছে, ওই ক্লকের কাছে পরে যাচ্ছে এই পার্সনের কাছে, বিকজ অফ রিলেটিভ মোশন. So there is a problem when the motion is along the same direction, which have to be readjusted again. So আমি ক্লক সিনক্রোনাইজেশন যাচ্ছি না, যদি কারো পার্টিকুলার ইন্টারেস্ট থাকে we can discuss it, but that's not the main theme of our course, because our course is mostly about electrodynamics, and relativity is a tool to help the subject. So relativity is not our focus, it's a tool which you are going to use to understand electrodynamics. Okay, fine, since you have a class, so I am stopping here. Maybe we can continue our discussion in tomorrow's class. Okay, thank you. Any question? Quick question? Okay, fine. If not, okay, we can continue tomorrow. Fine.